This is the 4-4 and 4-7 review. Calculators are allowed, and this is number 9. So with number 9, we want to find the maximum value of the derivative of this given function. So on all three of these, we're going to have to compute the derivative before we try and maximize the derivative. So for part A, f prime is a 24x minus a 3x squared. To maximize that, we need to take the derivative again to find the critical values of f prime. That will be a 24 minus a 6x. Set that equal to 0 or undefined. The only location is at x equals 4. So let's verify really quickly that f double prime changes from positive to negative. Prior to 4, say at 0, that's a positive number. After, say at 20, that's going to be a negative. So we did indeed get a maximum on f prime at x equals 4. The question is, what's the maximum value of the derivative? So I've got to take that 4 and plug it into the derivative. So f prime of 4 will be 24 times 4 minus 3 times 4 squared, which ends up equaling 48. Part B works exactly the same way, except now we're looking for the minimum value. So again, I have to compute the derivative. That will be 5 times the cosine of 5x. And then from there, I need the second derivative, which will be negative 25 times the sine of 5x. I need that to be 0 or undefined. It's never undefined, and it's 0 whenever the inside, which is 5x, equals a multiple of pi. Because remember, sines will equal 0 whenever the inside of the sine is a multiple of pi. So that means x will be a multiple of pi over 5. So some of these might be maxes, some of them might be mins. We will discover a couple of them. Let's say we let k equal 0, and then k equal 1, and k equal negative 1, and we'll just check to the left and right. Prior to, or between 0 and pi over 5, say pi over 10, we'll be looking at the sine of a pi over 2, which is a positive 1. That makes it negative. After pi over 5, say at 2 pi over 5, nope, that's going to be, let's do 3 pi over 10. So 3 pi over 10, if I plug that in, I will get a 3 pi over 2, and the sine of a 3 pi over 2 is a negative, times a negative will be positive. So here we're getting a minimum value, which means to get, or minimum location I should say, so to figure out the value of the derivative at that location, I will plug that in. So f prime of a pi over 5 is 5 times the cosine of pi, which is a negative 5. So the minimum value of the derivative will be negative 5. Last one, part C, the minimum value of the derivative again. So I've got to compute the derivative, which requires the product rule. So I have the first one times the derivative of the second one, plus the second one times the derivative of the first. Before I take the derivative, I'm going to simplify that and pull out the e to the negative x, and I'll see that I have a 1 plus a negative x, or a 1 minus x. Now I want to minimize this, so I will take the derivative again. First one times the derivative of the second, plus the second times the derivative of the first. I need to know when that equals 0 or undefined. So to find that, I'm going to factor out that e to the negative x and see what's left. This gives me a negative 1. This one gives me a negative 1 times that 1 minus x. So if I simplify, I'll have an e to the negative x times, it looks like a positive x, negative 1 minus a 2. So I need to know when that equals 0 and when it's undefined. Well, it's never undefined, because exponentials and polynomials never have problems. It equals 0 when x equals 2. So let's verify that that's the location of a min. So I'm looking at f double prime plugging in a number smaller than 2 and bigger than 2. If I plug in 0, let's say, this would be a 1, and that will be negative. If I plug in a 3, this will still be positive, and this will be positive. So I got a min at 2. The question is, what's the minimum value of the derivative? So I'm going to evaluate the derivative at 2. So I plug negative 2 in, I get an e to the negative 2 times a 1 minus a 2. That is a negative 1 over e squared. And I don't know if I left it that way or if I gave you a decimal. It looks like I left it like that, so we're good at this.